Hi everyone, welcome to this session with Hewlett-Packard Enterprise and NVIDIA. My name is Jordan Nanos and I'm going to be talking to you about AI's toughest tasks. Specifically, we're going to walk through some lessons of scaling enterprise AI from edge to exascale. When we were designing this presentation, I was talking to others that I work with, and we got the idea that basically we feel like we're Mike Rowe from Dirty Jobs sometimes, where there's so many interesting things that we use or that we do while working on delivering high-performance computing systems for AI. And we want to talk through a lot of those details today. So hopefully you're excited to come on that journey with me and learn a little bit. The first thing to point out in this presentation is really that though I'm going to focus on a lot of details of what it takes to deploy GPUs at scale and make them useful, HPE offers joint solutions that are developed with NVIDIA that are comprehensive. They include the compute, storage, network, system software, orchestration software, application software, and professional services required to take you from concept and design all the way through to a working cluster for AI inference or AI training. The obvious one here on screen is HPE Private Cloud for AI, which we've developed in conjunction with NVIDIA. And it comes in a set of prepackaged t-shirt sizes, small, medium, large, extra large, to really simplify the what it takes to get AI running in a private environment. Like I said, this is a comprehensive solution, right? We've designed this to get people started and to grow over time. In addition, we have a curated set of solution accelerators that are applicable for specific tools and frameworks, such as the NeMo guardrails, customizer, evaluator, as well as NVIDIA NIMs built into the platform. And we've also got a number of vertical industry accelerators that will get organizations started with their AI applications. But I want to start the core contents of the presentation with why. Why HPE for generative AI? In a word, private AI services from HPE are providing our users with control over their AI applications in terms of their data that they're using, the performance of the models, as well as their costs. There's a lot of regulatory requirements that many organizations contend with, compliance with intellectual property and copyright protection, as well as privacy and security guarantees that sometimes get thrown out the window if you use public cloud services. Private cloud services allow you to maintain control over this data because the infrastructure is running in a data center or a co-location facility that you have full control over. With model performance, this is in terms of both speed and model quality. When you own the weights of the models that you are running, you are able to fine-tune them, you're able to monitor what people are doing, and you're able to improve speed and reduce latency over time since you control the hardware and the configuration that you're actually deploying the model on top of. If you would like to tune an endpoint to improve performance in terms of throughput and trade off interactivity or latency, you can do that, and vice versa. In addition, model performance in terms of the end-to-end user experience can many times require integration of private data sets, which you can do without taking on risk, calling back to the control over data point. And finally, with costs, when you control the model endpoint that you're running on the GPUs that you have, there's no surprise bills for data egress or bursts during busy times when more GPUs are consumed. And obviously there's no software licensing that's charged per token or per user in order to, and basically that grows over time. By emphasizing solutions that are built on open source tools, open source models, and open source software frameworks, we're preventing developers from being locked in to private AI services. So that's why we're doing this presentation. The contents of the presentation that I'm going to go through now cover the 12 steps, as I see it, that we really actually use when engaging with customers who are interested in building out AI systems really powered by GPU clusters. You can see the contents on screen. I'm going to walk through them one by one and kind of describe the approach that we would take through this 12-step program, from sizing and design all the way through to expansion and future planning. So let's get started. The first piece here is sizing and design. And in my experience, there's basically two ways that this happens. Either an organization already has a GPU cluster or an understanding of the compute requirements or how much infrastructure they can deploy in their environment. And what they're really trying to do is onboard a new application. So either expand the cluster, build a new cluster, or just understand how the cluster is going to be used. In that case, the situation is something like, hey, provided a given application with certain characteristics, how many GPUs am I going to need to run this application? That's the type of question that we get. The second approach is not tied to an application at all. Instead, it's just all about accommodating for future growth. In these scenarios, questions are more related to the scenario where you have a given amount of floor space, power, and cooling, and you're just trying to fit as many GPUs as you can within the data center. These are two very different questions. I'm going to give some examples of approach number one in the sizing and design section of the presentation here, just because I think it's more instructive. But we see a lot of cloud service providers and many organizations, businesses, who are building IT like a cloud service provider, basically just building a factory full of GPUs on the data center floor for approach number two. But okay, approach number one. I want to start by giving an example of a sizing that I performed just a few weeks ago for a customer who's interested in automatic speech recognition, speech to text. The situation they have is that they collect about 500 gigabytes of audio every day that needs to be transcribed. And they know, or we know generally, that 1 megabyte of audio is about 1 minute. And so they're recording about 500,000 minutes per day using their audio recorders. We also know that one of the target models we're working on is the NVIDIA Parakeet RNN, 1.1 billion parameters. It's at the top of the Hugging Face ASR leaderboards. We know it's a good model. And from NVIDIA benchmarks, which I'll show in a second, the RTFX of that model on an A100 GPU is 2053, 2053. RTFX is basically a factor that shows us, for the amount of audio transcribed per second by the model, how many seconds of GPU time am I going to be using for compute. So in this case, since we have 500,000 minutes, we're going to divide it by the 2053 RTFX to get a total of 243 minutes of GPU compute time, or around 4 hours, for us to perform the daily transcription on a single A100 GPU. Now, there's a whole bunch of ways in which this can change. The source for the benchmark is one of NVIDIA's blogs, which you can click on and see more details on here if you're working on a similar problem. But the example is meant to show a framework, right? We can extrapolate these by testing performance on the H100 or the H200 or other GPUs in the future. We can also change the model. We can change the amount of data. There's all sorts of things we can do to perform the sizing, but we wanted to be able to assess for this customer, hey, a single GPU, we think we can do this transcription overnight. We don't need to build a massive cluster for this individual application to run transcription in a batch. Example number two of sizing here is retrieval augmented generation, very popular application. We know a number of customers who are rolling this out across their organization after building some demo applications over the last year or 2 years. And in this case, we knew some things like they're trying to roll it out to 500,000 users. Initial testing is showing that users submit an average of 6.4 requests per hour, which means about one request every 10 minutes per user. We'll need to support at least 562 concurrent requests per second with the cluster to meet this amount of average requests per hour. And the access pattern for the application is pretty consistent. Since it's RAG, we have 2048 input tokens and 128 output tokens. And finally, we're targeting the model Metalama 3.3 70B instruct. For sizing, I'm specifically, in the case where I did this sizing, the latest version of the LLM was 0.6.4, and with certain tuning parameters that favor throughput, so because it's an online batch application here, no real-time requirement for interactivity. We can achieve 3.45 requests per second per GH200 system, in this case the DL384 server from HPE, while deploying the model in TensorParallel 2. Need room for that KV cache for this batch throughput-oriented use case. So a quick sizing says that 562.5 divided by 3.45 means we need 163 of these DL384 servers, each of them with 2 of the GH200 superchips. As an aside, if you're interested in LLM inference sizing and planning for the future, I'm not going to cover it much more in this presentation. I'm going to get back to, what it takes to deploy these clusters at scale. But there's a lot of things that can change. Reasons you have to consider whether you should undersize or oversize. Reasons to undersize, well, models are getting smaller while maintaining a constant quality. New GPUs are supporting lower precision data types, float 8 and float 4 in the tensor cores for the Hopper and Blackwell GPUs, respectively. New quantization strategies are being developed to prevent quality loss in the models, as well as quantization-aware training. So we see more models being released with the float 8 data type natively. We've also got new improvements in the runtimes like VLLM, TensorRT LLM from NVIDIA, Hugging Face TGI, Llama with Llama CPP, SGLang. There's lots of options to improve throughput and interactivity over time. On the contrary, reasons to oversize and get more GPUs, I think, are more compelling personally. There's more users that are onboarding to these applications over time. There's more requests from each user as they learn to use the application well. New applications are getting developed that are powered by the same endpoint. That Llama 3.3 70B instruct model can probably power other things like a coding assistant or some sort of document summarization or translation application, or even just a generic chatbot, just as it helps the RAG application work as well, powers the RAG application. For RAG applications specifically, we're seeing input sizes grow over time since these models have large context windows, or you want to improve the speed of retrieval, or embedding models are improving to make faster retrieval possible. We're seeing that more and more context is being stuffed into the context window beyond 2048 tokens, possibly in the case that I was just showing, as well as growing output sizes. The reasoning models imply that there's probably going to be a lot more output tokens than 128 in an average RAG application going forward, if you're using models inspired by DeepSeek or O1 from OpenAI. And finally, the highest quality models just keep getting bigger. We previously were thinking that Llama 3.145B was the biggest model out there. There's now a lot of use of the 685 billion parameter version of DeepSeek, and expect more models in the 100 to 200 billion parameter range as well over time. If you're actually sizing for a specific LLM inference application, we've got this example chart here so that you can see what sort of inputs you might want to collect from a user community if you're thinking about deploying an endpoint. Things like which model is actually being used, the context window size, which hardware you're targeting, the usage pattern, any performance requirements or SLAs for the users in terms of interactivity or throughput, tuning parameters that you think you'll be able to apply, and then the result at the end, how many actual copies of the model you may need on a given GPU that you were targeting. In this case, since my simplified examples were all for inference, we really did not consider interconnect for sizing and design, which is a big thing to consider. We just really considered the rack and floor layout. How many racks do I need? Where are they going to go? The power consumption, so a design from the bus bar to the PDU. Power cable layout, meaning how many receptacles do I actually need per rack in my PDUs. The front-end network switch and cable layouts for north-south or data traffic, and as well as the place where you're going to connect to the shared storage, and then the out-of-band management switch and cable layout. Interconnect layout and bandwidth is probably the biggest thing for training clusters to actually get right, as well as, of course, login, scheduler, management server infrastructure that's not got GPUs in it, and then sizing and performance for testing the shared storage. The reason I say it's the most important thing, I'll just show a quick view of what the logical interconnects look like for a large training cluster. This is a design that we have done at scale for some of our largest customers. And you can see specifically each one of these racks, which is really a leaf switch, 001, 002, has an uplink to a spine switch in this design. And we effectively have 4 pods or islands with thousands of GPUs in them. The cable layout and the design to get the interconnect to work between those individual leaf switches and really the nodes under the leaf switches and the GPUs in those nodes being able to talk to every other GPU in the cluster is a massive design consideration when you consider scaling beyond a 3-layer fat tree. Moving on to part number 2 here with integration and planning. The big thing that we do at this stage is really take whatever design was, completed for the layout of, everything I just covered, and actually build it into a data center. So this is an overhead view, kind of a simplification for a data center that's going to host many thousands of GPUs. Specifically, there's different data halls here where you can see 2048 in the green at the top, 2048 in blue, 1024 in orange, and 2048 in red. This is obviously a plan for 1,000-watt GPUs to actually be deployed in a large facility, whereby we're effectively accommodating the build out of B200 GPUs with an overhead view from the data center above. When it comes to actually delivering those racks onto the floor, there's a big consideration for integration and planning at the individual node level, which is to say, if you partner with HPE, we have something called the Advanced Integration Center where we do all of this work in the factory so that you can do a lot less setup when it comes time to actually roll racks on site and light them up. What this means is that we set up the racks themselves by custom slotting components in the systems and placement of the systems in the racks. We'll even do things like labeling cables point to point and test the functionality of the interconnect so we know that all of these individual components are working in the factory before it gets shipped out. For advanced cooling systems, which I'm going to get into later in the presentation, we also test the direct liquid cooling loop from the manifold to the systems for leaks, detach and fill the tubes with liquid glycol in this case, and then install the CDU either in the rack or in the row, depending on which option we've got to go with. For individual systems, we configure the BIOS and firmware on the individual system so that it can boot at best performance and match the actual, the BIOS settings will match what the system's going to be used for. We'll set up the local drives for booting an operating system with RAID and any scratch data devices to be resilient, like with a RAID 5 or RAID 6 layout, and mount them to the operating system, assuming that the operating system is loaded in the factory. If the operating system is loaded and we have that version of Ubuntu on there or whatever it is, we may also configure specific site network settings. This is particularly important for brownfield deployments where there's existing expected prefixes for the host name, an IP range that you're going to be using, subnet mask, DNS server information, NTP domain, things like that. In addition, there may be individual software applications that are loaded in here. This is system-level software, like our high-performance cluster manager software that is installed on the head nodes to actually do the operating system provisioning, system monitoring, and in some cases, integration with the job scheduler to monitor performance. And then finally, mount points. Many existing systems will be, or many new systems, new GPU systems will be going into existing environments with existing file systems. And so we can create those mount points already with that information loaded. What this looks like in practice is that we have a questionnaire we work on with customers. I took a little screenshot and put it on the right side there so you can see a little bit of the Excel that we'll have to work with here. Excel is the disease you die with, not from, just like Bash. Okay, continue on with integration and planning. Another example is the Smart CID that we fill out. This is a customer intent document for the private cloud AI service specifically. As I build through this, you'll see, we're just filling in outside of Excel in a nice web form, the information that we need to actually load the system with the configuration in the factory that's expected in the data center that it's going into. So in integration and planning, when we're actually doing this work in the factory, why does rack layout matter? On screen, I've got some pictures of the racks that we had on site at Supercomputing 24 in Atlanta. And so you can see some nice, cable layouts here, and the liquid cooling loops for some of our fanless liquid cooling solutions on the right side there. Why does this matter? Well, I'm showing you good pictures because it matters when things don't go correctly or they're not done according to plan. And so on the left side, you'll see an HP recommended approach to cabling up some GPU servers. And on the right side, you can see an approach that one of our customers did, where you can basically see that the alternative approach can impact serviceability. You want to be able to pull the systems out of the rack, pull components from the systems, and service them. And so basically cable management is not just nice to look at, it impacts your speed to replace a component that's down if something happens during the operation of a cluster. Another example that can impact serviceability on the left, where cables are not being tied off and run on the rack on the left side or the right side. This can again impact serviceability. It can also impact the ability to perform upgrades where new systems are being integrated and you need to use empty ports on switches. Having proper labeling and being able to trace cables through the environment is a recommended approach here. Finally, some of these alternative approaches outside of serviceability can impact airflow. So a recommended approach here is to really just not remove any of the panels that you don't want to remove. The orientation of systems in the rack can impact this, but you want to guarantee that you have enough airflow for some of these very hot GPU servers if you're still using air cooling for some or all of the cooling on the system. At scale, this isn't just one or two racks, but even for just a 6 rack system that we've got with cable trays here on the left side, we can offer a 3D model of the cable layout to make it easier to plan exactly how long things are going to be and where they're going to run in the data center. Well, this can be really important at scale where so many cables are being run between racks that we need to use reinforced cable trays overhead to be able to handle the weight of these cables. And just look at the size of these cables here. It looks like a fire hose. Okay, moving on to step 3, which is site prep. Assuming that you've got a properly designed cluster for the inference or training workload that you're pursuing, you've got the design really available for the on-site integration, and it's been built at the factory correctly so that it's got all of the configuration that's expected. Preparing the actual site it's going into is also something that's important. So we will do things like site visits and just work with our customers to prepare the site and do things like plan for the modern power cooling requirements that we're going to have for these new racks, as well as integrate a new site if it's a brand new data center to meet the company access and security policies by setting up a VPN router, helping to migrate data, and verifying compliance with regulations. I'm going to spend some time talking about modern power and cooling requirements here because I think it's a big, really important topic for adopting the latest GPUs. In this case, air and liquid cooling has many different options, and specifically, a lot of our customers are moving from old single-phase or 3-phase 4-wire 208-volt to the new modern 3-phase 5-wire 415-volt power delivery to the busway. And they're also having to account for power spikes over the rated power consumption, where, for example, an NVL72 rack, though it's rated for 130 kilowatts, can spike to 192 kilowatts in real, measured power consumption. So for those who don't know or maybe interested in learning more about this, on the left side of the screen I have a picture of a single phase drop from the busway to the PDU in the rack. And on the right side I have a picture of a 3-phase drop. And both of these are actually not the 5-wire that I was just describing as more modern, but it's meant to demonstrate that for a given busway, there's only so many tap-off boxes that you can fit on there. And if a single tap-off boxes is feeding to a single PDU, and a single PDU, for example, only consumes up to 17.2 kVA, 17 kilowatts, to power some of the larger racks that we have, which are 40 kilowatts to 80 kilowatts, we actually need multiple drops to multiple PDUs in the environment to actually be able to consume this. And even existing modern busways cannot just fit enough of these tap-off boxes to be able to run the power available, even if theoretically you can drive that amount of power to the busway. The reason I say this is because the average enterprise data center, according to the Uptime Institute, still runs at 9 kilowatts or below. That's 75% of all data centers globally, if you consider the 2022, 23, and 24 surveys from the Uptime Institute to be representative. Less than 5%, much less than 5% of the industry is able to run average server rack densities in the data center above 40 kilowatts. Why does this matter? Again, building back to why we care, because individual systems with 8 GPUs are massive power hogs. The DGX H100 is rated at 10.2 kilowatts. And of course, HPE's HGX H100 system consumes similar to that, the XD670 or the XD685. And as we build for more powerful GPUs for Blackwell and beyond, there's just going to be more power consumption over time. Basically, GPU servers need more than 9 kilowatts per rack. Most designs that we have are for 4 systems, 40 kilowatts per rack. But there are designs for 80, 135, and 400 kilowatts per rack available from HPE. The next point of that is, of course, the cooling capacity. So if you can power that rack, you also need to be able to cool it. In purple, you see traditional approaches on this chart for cooling with water at the perimeter of the data center. Meanwhile, in blue, we see an introduction of liquid cooling where water is closer to the racks. Closer being, a whole range of different options, from hot aisle containment, cool aisle containment, to rear door heat exchangers, to a closed loop cooling solution that we call ARCs for full containment, and also DLC for direct to chip liquid cooling. The x-axis of this chart shows the cooling capacity per rack growing over time, and the y-axis shows a rough density and cooling efficiency metric, which is to say, the more liquid cooling that you use, the more efficiently you will be cooling these systems, and the better your total cost of ownership will be. In practice, we end up combining a lot of these technologies where we will use direct liquid cooling to cool most of the system, and then some combination of air cooling, rear door heat exchangers, or ARCs to actually get the rest of the heat out of the system. If you'd like to learn more about this, a lot of organizations are now designing entirely new data centers just to host GPUs, and I'd suggest you to learn from my former colleague Wade. Wade gave a great talk at DCAC 2024 where he goes through what it takes to design a data center for GPUs today. But I mentioned an important word before doing that, which is TCO, or I guess it's TLA, a nice 3-letter acronym. The question we have is like, okay, if I'm going to make this upfront investment, I'm going to bring in electricians and people to work on plumbing, when will we make money back on that investment? What is the total cost of ownership? And we built a calculator for this. I'd encourage you to reach out if you want to do this for your individual application. I blurred out some of the details in here because it includes some specific pricing. But basically, what did we consider in this calculation that's on the left side of this chart? And it's usable for anybody who wants to do this calculation for themselves. Just get this information. And you need to really consider the price for everything, not just the systems, but even the cables, if you want a total TCO calculation. But the typical payback period that we've seen with this is about 7 months, and the result is pretty staggering when we consider the costs associated with cooling being about, in this arbitrary example, $367 per year. Whereas if you're using liquid to air, it goes down to $289, and if you're using DLC, it goes to $39. DLC again being direct liquid cooling, where you're getting air off the chip. Okay, moving on to part 4, where we actually build the system in the factory and test it. I'd just like to highlight that many customers of ours have access to systems remotely or visit our site during the factory build process. On screen, you can see a nice picture of Jensen Huang, the CEO of NVIDIA, and Antonio Neri, the CEO of HPE, with executives from the Department of Energy at the U.S. National Lab, Los Alamos National Laboratory, accepting a system called Venado and cutting the ribbon, I guess. Why do I think this is important? I think the biggest reason is the new framework for artificial intelligence diffusion that's been released by the U.S. government. Having a secure manufacturing facility available in our Chippewa Falls, Wisconsin location allows customers to have guarantees around the provenance of the system and its security, which is how we serve many of the national labs like Los Alamos. Lonel is also doing something interesting here, which is they're using this Venado system to run the world's best language models. Yes, OpenAI has reached an agreement with Venado to install its latest series of models, the O1 and O3 series, on the Venado supercomputer. And they know that this system preserves privacy. As I've been saying at the beginning, HPE is all about private AI. The other thing about this is that this system itself, Venado, is 100% fanless, direct liquid cooling, and that rack on the previous slide, each cabinet is 400 kilowatts. So much bigger than the average data center of 9 kilowatts per rack today. I'd encourage you to watch the replay of our AI day, where our CEO Antonio and many of our executives gave more details on this direct liquid cooling architecture that we've got, and did an interview with CNBC describing this, which I've linked on screen. Step 5 here, of course, is on-site integration. So assuming that the system has been built, tested, and shipped from our factory with the relevant configurations completed, actually integrating it on-site can involve placing the racks on the floor, uplinking to an existing network, connecting to file systems, setting up authorization and authentication for users to access the system, and then for DLC, connecting that coolant loop I said would show up filled from the nodes to the manifold in the racks, so that it's quote-unquote plug and play. The manifolds being connected to the CDU in rack or in row, both options, and then the CDU being connected to the facility chiller in the event of liquid cooling. You'll see on screen a quick screenshot of a document that we provide with all PCAI systems, providing the details for the environmentals and the power and network requirements. This is a small piece of the document, but I wanted to share that even for a single rack, air-cooled, standard, 8 GPUs, let's say, we still provide all of this information to make sure that the delivery of the system goes smoothly. Step 6 is where we get into software. So assuming that this all goes well, it's on site, it's connected to power and the network, users can access the system. What comes next? Some of the software could have been loaded at the factory, but basically the system software, like our performance cluster manager software, which I've got a YouTube video linking to a demonstration of this on screen, is used to deploy or provision the compute nodes. In many cases, we can use virtualization technology to actually deploy the compute node machines as virtual images as opposed to bare metal images. Fabric Manager may be installed, UFM for InfiniBand, many alternatives for Iraqi v2 network. Login and code development nodes so that people can connect in their VS Code remote or other access systems to get into the cluster. Upload their SSH keys, things like that. And then storage, mounting POSIX file systems, NFS, Lustre, things like that, as well as providing S3 access keys if there's data on S3. System software kind of builds up like a stack, right? We start with physical infrastructure, we build hardware components. The three key components of a system software is the operating system, the drivers and libraries that are installed in that compute node image, and then the management software that's managing those actual OS images. On top of that is the next piece of my presentation, which is orchestration software. All of this together builds an IaaS solution, infrastructure as a service. The same experience you would have if you're getting a VM in AWS, right? Except in this case, you're accessing, a cluster, right? On top of that, to build platform services, we actually install machine learning applications. In this case, the PCAI product I referred to at the beginning of the presentation has a lot of these applications pre-installed. And so we think of that as PaaS, platform as a service, where users are not accessing the system over SSH or kubectl or running any srun or salloc commands. Instead, they're accessing the system with their browser to a Jupyter notebook, right? That's a very different experience, and it's something that I would differentiate between whether you're consuming an IaaS solution from HPE or a PaaS solution from HPE. Of course, on top of that platform software is where we build things like we bring in the foundation models, we bring in the backend services, customize them, and then we have model services as an API so that we can build, first of all, trustworthy AI applications on top, but then actually get the business outcomes where we are getting code generated for us, we're getting assistant with research, we're answering RFPs, something like that. Okay, step 7, assuming that system software is installed and there's a cluster to access, is really making a decision about that orchestration software that's being used. I think a lot of traditional organizations who come from an HPC world have an opinion on this, and then a lot of cloud native applications have a different perspective on this. So in this case, orchestration software really allows for two primary different options based on the three user personas that I'm describing on screen here. The first option is Slurm. Slurm is built for batch jobs and can also run interactive notebooks. SBatch for batch, salloc, and srun for interactive jobs. So users who want to run large jobs like train models, fine-tune models, run batch inference, prep data, things like that, they can be supported on this cluster. And then users who want to interactively explore data, build a model with a training script, run code, see a result, they can work from the notebooks section with salloc. The other option is Kubernetes. Kubernetes, because it's cloud native, is built for microservices. So users who want to deploy trained models as a load balanced inference API, they want to run a database, maybe a vector store. They basically just want to share data with others and provide observability into what's going on. They're going to be using Kubernetes. It's really, really not good to run load balancers on Slurm, I would say, in my experience. Kubernetes, of course, can also run with deployments for notebooks and things like that, so that you can have an interactive workload. But there's a big difference here, right? Slurm is not good for microservices, and Kubernetes is really not good for batch jobs. I would say that Kubernetes is possible to run batch jobs with tools that provide the resiliency and the gang scheduling and all sorts of other features on top of Kubernetes to make it work for batch jobs. The other thing is really not possible. Making Slurm work for microservices, I would not recommend. Those tools might be something like the Kubeflow, MPI operator, Ray, Spark, Dask, things like that can be deployed on top of Kubernetes with a Helm chart. What this looks like at scale is application software. So on screen, I'm showing you an example from HPE Machine Learning Inference Software. This is an application that we provide for users who are deploying models on top of the PCAI product. Instead of working directly with Kubernetes and Kserve, instead you get a nice application where you can click to start and stop a model endpoint, decide which model you're going to use, configure access tokens for users and groups to access the model API, monitor who's using what, track logs, all sorts of different things. This is the sort of experience that many machine learning developers will be used to using on a GPU cluster. They don't want SSH, and they don't even want kubectl or srun. They want to be able to call an API, a REST API, or click on a UI to deploy models and then start building applications on top of them. Another example is, the application where end users might consume the models. I've got a screenshot from OpenWebUI, a place where I do a lot of development with language models, where I generate code, where I, chat with PDFs. This application software is, again, open source. It's a Helm chart. You can run it on top of a Kubernetes cluster like the one that we provide with PCAI. Okay, step 9, assuming that we've loaded the software stack, those 3 different layers, is acceptance testing. So acceptance testing can be done for the hardware, for the interconnect, running sample jobs, and measuring performance. This is a big topic that I could spend time talking about with HPE and how we do it for many of the largest systems that we have, and just how talented the team is that works on this sort of stuff. But I'd like to suggest a few options for people who are getting into acceptance testing and trying to make sure that their cluster works properly. The first one is a networking benchmark that mimics the behavior of nickel tests. So you can test that the network is working well and performing at as you expect with full bandwidth. This is from a friend of mine, Stas Beckman, who developed an alternative to nickel test that runs with just PyTorch and the bundled nickel library inside of PyTorch. You can click on that on screen. I've hyperlinked it. Another one is GPU burn. This is a classic for acceptance testing of the physical hardware, so that you can know that you're not having failures in the individual GPUs and they're able to run at full power. And then nickel tests themselves. I provided a link there if you're interested in what that looks like. With acceptance testing for burn-in and validation, what you kind of see, I've got this great chart from SemiAnalysis here where initial failures can be quite common at the beginning of deploying a system. The guys at SemiAnalysis call these infant mortalities. Random failures are much less likely over time. And then at the end of the cluster, call it a 3 to 5 year life cycle, typically with warranty, is when you start to see an increase in wear out failures. One comment on this is just related to dedicated spares. During installation and acceptance testing for large clusters, HPE will bring a kit of dedicated spares, and having an understanding of the proximity to parts depots is an important, logistics concern. When you think about how many GPUs, network cards, power supplies, even motherboards can fail in clusters with thousands of GPUs in them, which is becoming just more and more common over time, right? Divide 1,000 GPUs by 365 days by 3 years. And if you expect a GPU to fail once during its 3-year life cycle, once during its 5 years, you could be seeing failures every day or every other day. The final thing here on real deployment and use of the actual cluster I've been talking about is step 10, failures and diagnostics. I would also call this day 2 operations, where we're monitoring the hardware and diagnosing failures. There's many different strategies for hot swap and cold swap nodes that can be considered during design and with the virtualization stack to be able to back up, expand, clone VMs in a very different way than it might work with bare metal, where you're just kind of provisioning images. And then also an emerging aspect of this is the ability to handle failures with resilient software for the training and infrastructure and inference level, effectively having the software allow for the treating of the GPU servers as cattle and not as pets. The simple example here for monitoring, I just again provided some links to a really important tool from NVIDIA, which is the Data Center GPU Manager, DCGM, to get access to what's going on with the GPUs on the system and the NVLink interconnect. For the third thing with handling failures with resilient training software, really important project that's being worked on by the PyTorch Labs community is to have per step fault tolerance for training, meaning that if you have a failure during training, you're not recovering from a checkpoint. Instead, you're accommodating for that failure. I think this is just so important from what I've been hearing from people developing this, and it's nice to see it break out of the frontier labs and really be used by and pushed forward by an open source community instead of being something that's considered secret sauce. And then finally, for inference, I was talking about MLIS. Probably the best option for running resilient infrastructure for inference over time and making these model endpoints load balanced, auto scalable, things like that, is Kserve. Kserve is just an excellent project on top of Kubernetes for inference. The last two steps here is future expansion, and future planning is my 12th one. So for expansion, I think the biggest thing that I've seen from organizations right now is trying to scale up. Like, we've got this application and then something happened, like I covered on one of my first slides. More users want to use it. The size of input and output is growing. New model comes out and I want to try it and it's bigger. For whatever reason, we need to expand the amount of GPUs that we have in the cluster. And I just want to point out that, first of all, considering this with switches up front is really nice, really important, because you don't want to have to recable everything. It takes down the whole cluster for sometimes days just to be able to run all the cables. But assuming that that's all done, a lot of people don't really consider load balancing, and I don't know why. So I pointed out an experiment that I ran here. It was really simple testing of the 70B Llama 3.3 model with some specific tuning parameters to get a certain amount of output tokens with a larger size, like a 4096 input size here. The testing that I did was basically just to show a simple load balancer, Nginx, powered by 16 copies of the 70B Llama 3.3 model, where 8 of them are running on H200s and 8 of them are running on H100s. And the fact that we can just serve the model behind that load balancer with those new GPUs and drive near linear improvements in performance, really without tensor parallelism for a model this size. I think a lot of people jump to tensor parallelism shown on screen in orange instead of using load balancing for smaller copies of the models. This here is an example with the 3.2 90B Vision Instruct. Sorry, my slide is wrong. Model there to show, load balancing is preferable for aggregate performance over tensor parallelism, both within a node and if you try to go outside of a node. Future planning, there's not much to say here, but I think for the rest of this conference, GTC is incredible to learn about the new technology that's coming. I guess if there's one thing to say, it's that we're going to see more and more specialization in the chips and more power to the chips. The future is hot and heterogeneous, and it's operating at data center scale. And on the screen here, Jensen's slide says it's a 1-year rhythm for new chips. So make sure that is considered. In conclusion, I'm going to finish with a little bit of what I started with. HPE has offerings like Private Cloud AI that simplify all 12 steps that I referred to throughout this presentation, from design to delivery, installing software, getting it in the hands of users, supporting it over time, and expansions. We've considered all of that for those enterprises who want to start out in private in this solution. It includes all sorts of NVIDIA software. It's built with t-shirt sizes so we can grow with you. There is another option from HPE that kind of fits in between the build it yourself with infrastructure and IaaS solution and the build with our PaaS solution, that PC AI offering. And that is what we call the AI Factory. This is a modular view of it. It looks something like this, where we build from the infrastructure at the bottom to the operating layer to deploy multiple Kubernetes clusters or multiple Slurm clusters through a control plane. We acquired a company recently called Morpheus with just exceptional cloud management platform. I encourage everybody to go Google Morpheus, check it out, and then deliver some of the AI workloads at the very top. Finally, considerations around security, lifecycle operations, and observability is something that our team working on our HPE AI Factory has really taken into account, and hopefully you can spend some time learning and understanding this stack. So I started with this question in sizing and design. If you were working on one of these questions, either supporting a new application, provided a given application with certain characteristics, how many GPUs do I need to run it? Or given a certain amount of floor space, certain amount of power and cooling, how many GPUs can I fit in this data center? How much is it going to cost? We're here to help. I'd be very excited to help you maintain control over your AI-powered applications with HPE for generative AI. Control over data, control over model performance, and control over costs. If you'd like to connect and learn more, I'm on LinkedIn. I've got a YouTube channel with some demonstrations. Maybe some of you are watching this video on this channel. I'm on X, I'm on GitHub. Please reach out and connect. Thank you for taking the time to learn a little bit about HPE and our contributions to generative AI in the marketplace.